Yeah, so this is the whole notion of Deep Space Nine. There's a wormhole, space is wrinkled, and so we can go, because you have this little problem with the speed of light. Or maybe they don't in Star Trek because they go faster than the speed of light, right? So this saves a lot of fuel because of all that, dilithium stuff or whatever, right? Okay. So now let's go to a finite. We could take that thing and spread it on the surface of a globe. This globe has like a crack in it. I don't think there's really mountains there in the middle of the Pacific. It's like somebody dropped it. He's got the whole world in his hands. Whoops. Here we go. Right. Okay. So anyway, this is a two-dimensional surface, right? Okay, it is finite. It is not infinite in size, right? Okay, it is finite. It is unbounded. In other words, we can travel in any direction and never run into a boundary and go, oops, better not go any farther, right? They weren't so clear on that in Columbus's time, apparently, right? There we go. So this is a finite, unbounded, two-dimensional universe, and this one has positive curvature. There's also negative curvature. We'll talk about that when we talk about the Big Bang. This one has positive curvature. What that means is that we can end up getting back to where we started. There's other implications of that. But that's when we talk about curvature of space. We're talking about these three dimensions curved in a fourth spatial dimension that we cannot conceive of, right? And so if we have, let's go back to the two-dimensional analogy, right? Okay, let's go back to the two-dimensional analogy. This is the notion, right, is that if we curve the space upon which massive objects try to travel, they end up going in a circle. It's possible to, right? This is the wrong shape of a bowl. And by the way, this bowl just lives in this cabinet. Whenever I need to, demonstrate this point, I just pull the bowl out. I don't know whose bowl this is. Some kid left it in my room years ago. Yeah. There you go. Right. This is the wrong shape, though. Gravity makes things that are shaped like this. They're bell-shaped, as in like bell of a trumpet shaped. Okay? Right? So the notion is that instead of force at a distance, it's just that the sun actually is bending space-time in such a way that the Earth, in trying to go straight, ends up curving around the sun, right? So the analogy was a sheet of rubber, right? We fill the room with water to this depth, stretch out a sheet of rubber, put a shot put on there, and it makes this distortion. Other objects trying to go straight near that bend in the space, right, in space-time, actually end up going in circles, right? Now, somebody asked a good question last period. They said, okay, well, so does that mean black holes only face in one direction? But understand, this black hole here this is a two-dimensional universe. It faces in all directions. You can enter it this way, this way, this way, and those are all the directions that exist. The notion that it opens in one dimension, or in one direction, is a three-dimensional interpretation of this, right? Now, what we're dealing with is that mass distorts matter, the three dimensions that we're aware of, around a fourth dimension that we can't picture. This is pretty hard to picture, isn't it? Right? So again, if you're a four-dimensional being, you go, yeah, it points in that direction, right? Okay, and of course you can interpret that as time, right? We're outside the black hole, we're inside the black hole. Yeah?
But wouldn't that make that an accurate analogy for a description of a three-dimensional universe? Wouldn't you need to rotate in all directions at the same time? Yeah.
Or something, yes. Yeah, this is where last period people were trying to picture it, right? And like some kids needed to go and buy new graphics cards for their brain, and like some kids said "ow" because they stretched a muscle. Okay, so here's a crazy thing: if this space that we're in, there's ways to test our space, and we've, by the way, we've done this test. I'll talk about this when we talk about the Big Bang. We've done this test, but the notion is, say let's go back to the two-dimensional universe, right? Okay, if you draw yourself a triangle, okay, and you look at the measure of the interior angles, you add them all up. Right, and you draw a thing with light, using light beams as the straight edges, right? And you add up the angles inside there. If you get, in flat surfaces, right, Euclid tells us that the sum of the interior angles is 180 degrees, right? But if there's positive curvature and enough of it, right, you'll get more than 180 interior degrees of angle. And in this demonstration, they've fit 270 degrees in there. But the sky's the limit. I mean, you could add up, not the sky, but you can get more than that or less than that. Right? You can't get less than 180 degrees, but you can get more than 270. And how you do this is, of course, you go up a particular line of longitude, right? You go along the equator some distance, right? Then you go up one of these lines of longitude, right, all the way to the North Pole, go through 90 degrees of longitude, right, and then go back down to the equator. You're always making right-hand turns, and it's adding up to 270. But you could just as easily go farther on the equator and have more than that, right? So it's not that they, on spheres it's always 270. It's just that it's more than 180. Yeah.
What would happen if you impose that on a plane or something, like you've shown a light, it was like a balloon or something, you've shown a light center, you impose it on like a piece of paper, would it have less than 180?
Well, then you get like a Mercator projection where it exaggerates, makes Greenland look bigger than, I think is what you're talking about, right? Those maps where Greenland looks bigger than Africa,
Yeah.
right? So if you're putting it on a flat surface, a Mercator projection is where you wrap this in poster paper where it touches its tangent at the equator,
Yeah.
right?
What would that make it turn into less than 180? What would that be?
I don't know, I have to think about that.
No, because wouldn't it either curve the lines?
Well, it would curve the lines probably, but I'm
Yeah, but they.
But if you had like a light and you've shown it out from
Here is the interesting thing that we've done. Okay, I mean, we're getting ahead of ourselves, but I said if you look back far enough, if you look far enough away from Earth, you're looking back in time. At some point, you see the universe when it first became transparent to radiation, right? So you see this big fiery wall, right? Okay, we know how big those features are on the big fiery wall because of quantum mechanics and causation and the speed of light, right? And so we've actually drawn triangles. It's like, okay, there's one feature on it. We make a triangle, don't we? Right? As far as we can tell, by the way, the universe that we can see, the observable universe, all the way to that fiery wall, is exactly flat. Euclid reigns, okay? And that's either because A is flat, or B, we're looking at such a small part of it that it just looks flat, right? Tualatin is regionally, is locally flat, right? But the Earth is globally spherical, right? So we're...
Locally flat, locally spherical.
That's right. It's like think globally, act locally, right? The physicist's answer to that is locally flat, globally spherical. Yeah.
Just a question. How is that, like, I know there are more theories than this, theoretical physics, with more dimensions. Is this kind of how...
Okay, so there's theories with more dimensions, and these are like the string theories and whatever. This is a classical theory, right? So this is not, classical means not quantum, not based on probability, but just a classical theory. This works really well until you get to a black hole where it generates infinities, right? And we need a quantum theory, right? But yeah, those other ones like string theory and all these things, right? And particle theory physics and stuff like that, those things are getting into higher dimensions. Now, here's the story, and this is, I love this story, right? Einstein is doing this, and he realizes that it has to do with curvature. Well, if it's curvature, we need 4 dimensions. So he starts doing math, and as you might imagine, it's somewhat difficult to do geometry in 4 dimensions, right? And so there he is trying to do all this math and stuff. And Einstein has admitted that although he's a really good physicist, he's not all that great a mathematician, right? Now, meanwhile, okay, over somewhere, I think in France, right? Okay, this guy named Riemann is sitting there, and mathematicians it's basically like they're weightlifters. They're just like, doing this with their brain is like, so he develops a 4-dimensional geometry. Riemann just independently has developed this 4-dimensional geometry, and everybody says, Riemann, there's only 3 dimensions, this is useless. And he goes, yeah, but it's cool, look at it. And he figures out all these transformations, all of this math you can do, right? And everybody's like, Riemann, there's only 3 dimensions. He goes, yeah, but look how big this muscle is in my brain right now, right? He's like this weightlifter, right? He puts this book on the shelf, right? Meanwhile, over in Germany, right, Einstein is trying to do this. He can't do the math. The math is too hard for him. One of his friends says, hey, this guy wrote something about 4-dimensional geometry. It looks like you guys are doing the same thing. Einstein gets the book, checks it out of the library, right, reads it. He does all the little exercises at the end of the chapter that Riemann has written, right, and learns 4-dimensional geometry according to Riemann, goes, this is it, figures it out, and this gets him over the block where he was, and he gets his theory of general relativity. This is an amazing thing. Isn't this amazing? So the next time, this is a famous thing. I don't know if you guys have ever followed this, but it's really popular to take some aspect of science or math or something like that, some part of pure research, and say, who cares about the endocrine glands of tree frogs in Brazil? Why are we spending $700,000 to observe the adrenal gland of a, right? This is a ridiculous waste of taxpayers' money. Notice I always have to use the old geezer voice for that. This is a ridiculous waste of my money. We should be spending it on jobs here in America, right? The next time you hear somebody criticizing that, just ask them the simple question. Just go, well, what will be the next scientific breakthrough? Where's it going to happen? Can you predict that for me? And they'd be like, well, I don't know. Well, okay, then how do you know that that's not it, right? Because this guy doing this obscure thing for no apparent reason ends up giving us a theory that is now well accepted, right? Another example of this is that the people doing particle physics, right, and these like superstring